Recent experiments at ETH Zürich have done something that sounds impossible. They have observed particle spin correlations emerging directly from the quantum vacuum. This suggests that visible matter might be born from nothing. But here is the real problem. The headlines are selling this as a breakthrough in energy generation, implying we are on the verge of a battery upgrade that extracts power from empty space. The truth is far more complex and far more interesting. By the end of this explanation, you will understand why this is not a shortcut to free energy, but a fundamental manufacturing challenge that pushes the boundaries of thermodynamics and requires a 50-year timeline to become viable. Let us start with what actually happened in the lab. Researchers at ETH Zurich utilized an optical cavity, a device designed to trap light between highly reflective mirrors. Inside this cavity, they placed a degenerate Bose gas and subjected it to a regime known as ultrastrong coupling. This is a specific condition where the interaction between light and matter becomes so intense that it fundamentally modifies the electronic states of the atoms involved. The vacuum fluctuations, which are tiny, random variations in the electromagnetic field that exist even in a perfect void, were seeded with external photons. These fluctuations acted as the catalyst for the simultaneous creation of atom pairs. The result was a vacuum-dressed state where particles appeared with correlated spins. This is the emergence the headlines refer to. However, the mechanism is not magic. It is a controlled thermodynamic process that relies entirely on the input of external energy. The vacuum fluctuations did not provide the power, they provided the medium. The energy required to maintain the cavity, to stabilize the lasers, and to cool the system to cryogenic temperatures is orders of magnitude greater than the energy associated with the zero-point fluctuations being harvested. In other words, the system consumes a massive amount of power to create a state where matter appears to emerge from the vacuum, but the net energy balance is deeply negative. Here is the thing that changes the entire perspective. We are not extracting energy from nothing. We are converting input energy into matter. The process is fundamentally a matter of converting the energy you feed into the laser system into the mass of the new atoms. This is governed by the equation E=mc². To create matter, you must pay the energy cost. The vacuum fluctuations merely lower the threshold for the interaction, acting as a catalyst, but they do not supply the fuel. The engineering reality is that maintaining these vacuum-induced correlations requires infrastructure that is currently incompatible with compact or mobile power systems. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider the stability of this system. The vacuum-induced coherence is incredibly fragile. It can be disrupted by the slightest thermal noise. To prevent this, the entire apparatus must be isolated and cooled to temperatures near absolute zero. This creates a massive infrastructure cost. You are building a cryogenically cooled cavity that consumes orders of magnitude more energy than the system yields. The rate of matter creation via these spin-correlated vacuum interactions is negligible on macroscopic scales. While the theoretical framework suggests potential for high-temperature superconductivity or novel material synthesis, the energy density remains too low for practical power generation. Now consider the gap between the quantum scale and the industrial scale. The experiments at ETH Zurich operate at the level of individual atom pairs. To generate a gigawatt of power, which is what a typical power plant produces, you would need to scale this process by many orders of magnitude. The current benchmarks show that the rate of creation is far too slow to be useful for energy production. The primary knowledge gap lies in scaling these microscopic correlations to macroscopic energy outputs without prohibitive infrastructure costs. You cannot simply turn up the dial and get more power. The system hits a wall of thermodynamic constraints. This leads us to the most critical insight. The leap from observing vacuum-induced correlations to a scalable matter from nothing battery is not a software update. It is a fundamental thermodynamic hurdle. The engineering constraints shift the problem from finding an energy source to solving a system stability issue. The vacuum fluctuations are not a free reservoir of energy. They are a quantum state that requires immense investment to access and maintain. The 50-year timeline for viable manufacturing is not an optimistic prediction. It is a realistic engineering constraint based on the current understanding of cavity quantum electrodynamics. The research from RxIve and the IOP publishing journals on the quantum vacuum supports this view. These sources confirm that while the vacuum can be manipulated to influence matter, the energy balance remains strictly negative for extraction purposes. The process is a controlled manipulation of existing quantum fields rather than a manufacturing breakthrough. The theoretical pathway for matter generation exists, but it operates strictly within the ultra-strong coupling regime. This regime demands precision and energy inputs that far exceed the value of the output. We must also address the misconception that this is a battery upgrade. A battery stores energy for later use. This process creates matter by consuming energy. The distinction is crucial. If we were to build a device based on this principle, it would not be a power source. It would be a power sink. It would be a machine that consumes electricity to create atoms, which is a fascinating scientific achievement but not a solution to the energy crisis. The potential applications lie in material synthesis, perhaps creating new superconductors or exotic materials, but not in generating electricity. The confusion between scientific discovery and commercial product reality is a common trap. Viewers often struggle to distinguish between new physics and new products. When a paper is published showing a new quantum effect, the immediate assumption is that it will be commercialized quickly. But the history of physics is filled with discoveries that took decades or even centuries to translate into practical applications. The transition from a lab experiment to a scalable industrial process involves solving problems that are not mentioned in the abstract. It involves cooling, stability, cost, and safety. The primary takeaway is that the quantum vacuum is not a battery. It is a complex quantum field that can be manipulated under extreme conditions. The emergence of visible matter from these fluctuations is a controlled process that requires more energy than it produces. The 50-year timeline is a reflection of the difficulty of scaling these effects to the macroscopic world. We are not looking at a future where we can charge our phones with empty space. We are looking at a future where we might understand the fundamental nature of matter and energy in ways that could revolutionize materials science. This distinction is vital for anyone trying to understand the trajectory of technology. It requires us to be honest about the complexity of the physics involved. We cannot dumb down the science to make it sound like a magic solution. The engineering constraints are real. The thermodynamic hurdles are significant, and the path forward is long and difficult. But that does not make the science any less fascinating. It makes the eventual breakthrough, when it comes, all the more significant. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.